Today we'll be talking about Kotlin and more specifically about domain-specific languages and how to use some different advanced techniques to make them cool. Just a few words about me. My name is Pavlo. I don't see the slides. Okay, cool, thank you. I'm Google developer expert for Android, and I also work on mobile infrastructure at Lyft. And yeah, so let's talk about the agenda of this talk. So first, we will take a look at some concrete example of a Kotlin DSL, because it's not sufficient just to see some abstract examples of how different Kotlin elements can be used for DSLs, but rather we'll see how everything together can be applied for some specific use case, so that we can see how it works together. But all the concepts described in this talk will be applicable to any kinds of DSL, including those needed for Android. And once we do this, we will just decompose and deconstruct our DSL into some small components and see how to implement each of them. So a concrete DSL example. Our DSL will be a Starlark code generator. So don't be scared about the word Starlark. This is a programming language which is dialect of Python, and it's basically used as a scripting language for Bazel build system. So similarly to how Gradle uses Groovy and Kotlin scripts for writing some script configurations, Bazel uses Starlark. But in the context of this talk, let's just think that all code that we see that works with Starlark, let's just assume it's all Python code, because it's very similar, especially in the context of this talk. So yeah, and you might ask, okay, so why would we need a DSL for a code generator? And the idea here is that our DSL will replicate the syntax of a Starlark language. So basically the code that we are writing in Kotlin will look the same, almost the same as a result in generated Starlark code, which provides this declarative approach for code generation. And yeah, if you're interested to see more source code of this DSL, feel free to go to the GitHub. It's part of project Iron, which is like a project for automated migration from Gradle to Bazel build systems, and this DSL is used to generate some Starlark scripts. All right, so yeah, let's see how does this code generator work. So here we can see some example of a simple Starlark code, and again, let's just assume this is a Python code. So here we have some variable and we have a variable assignment, and then we have an Android binary function, which is just regular function call. And in context of Bazel, all this does is creates a buildable target so that we can run and build our Android application with Bazel. But yeah, just let's assume this is just random code on Python. And here is the DSL that we have for it in Kotlin. So just once again, here is the actual code, Starlark code, and here is the DSL which might generate it. As you can see, it looks pretty similar. Of course, it won't look identical as in an ideal world, because Kotlin still has some limitations in terms of building DSLs. But the idea here is that what we're writing in this DSL should be generated the same way in Starlark. And as a result, when this DSL is written, we can just put everything, all of it in some variable like Starlark file, and then we just write it to the file system. And yeah, this is the idea. And the way how it works under the hood, just briefly, it works similarly to how regular Starlark interpreter works. It builds all the components of the language and of the syntax into some tree data structure, which is called abstract syntax tree, where each component of the DSL of the language is represented by its separate tree node. And when we have this abstract syntax tree, it's very easy to generate fancy, formatted code, which is something that we expect as an output of our program. So yeah, let's see how this maps together. So on the left we have the part of the DSL, and on the right we have the tree that it generates. So for example, we have an Android binary function call. And for this, we will have a separate node in our tree, which is called function call, and it has name Android binary. Similarly to an argument, so we have an argument which is called name, and we have its value, which is app. And app is a string literal. Yeah, so as you can see, for every part of this code, we have a separate node. So the same thing works for manifest argument. Sorry. And the sources works a bit different. It's like a more complicated case, because here we have like binary expression, like this plus operator. And the way how it works, we have a separate node for this binary expression, and it has reference to its left operand and its right operand. And on the left we have a list expression, which inside has another node, which is like a main activity, which is something that we put as a string. Yeah, so this is briefly the idea of how the DSL works. And again, when we have this tree constructed, it's then pretty trivial task to generate formatted Starlark code. And yeah, for each node of this tree, we will just have a class representation. So for example, we have a root node, which is Starlark file. Then we have a function call, which will have another node. Then we have like argument, for example, and we have many more. This is not a like complete list on the screen, but yeah, the key point here is all of them implement some generic node interface, which means that all of them are part of the tree. So yeah, this is like a brief idea of how it works, and now let's see how to use different components of Kotlin to actually achieve this. So first, what we need is to actually enter the context of DSL, because like we're adding some new functionality, kind of new like domain-specific language, and these rules might work not everywhere in the program, but somewhere. So in this case, we need to kind of enter the DSL context, and we are doing it by having this like build.bazel function, and you might see that the function name is a bit weird because it has a dot inside. And why it's called build.bazel? Because this is the name that Bazel requires for you to have to include the code of Starlark. So every file with Starlark will be called like build.bazel. And the way how it works, we can, from the implementation standpoint, we can have an object which is called build. And then this is like a dummy object, just like to have this, to look fancy. And then we just create an extension function to this object. And the key point here is that since we need to enable functionality of our DSL, is this body parameter, which is itself is a lambda with receiver, which basically this is the function that works kind of as an extension function to some specific type of object, which in this case is Starlark file context. And this Starlark file context will provide all the operators and functionality of our DSL. Yeah, and as a result, we are returning the Starlark file class, which is, again, just a reminder, a root tree node of our abstract syntax tree. And if we're going back to the like front-end part, to the actual DSL, inside of these curly brackets, we'll have this as Starlark file context. So every function, every operator, everything that's available as a member of this class, an object will be available inside of this DSL. And for example, here we have Android binary function, which is already a part of DSL. Yeah, and inside how this Starlark file context works, yeah, it has defined like Android binary function, and it has something called statements, which is a mutable list of nodes, which basically means that it will just hold the subtree, but actually the tree, abstract syntax tree of the code that we need to generate. And every function will add something to this tree. Okay, so first component that we need to implement is function calls. So for example, here we have a Starlark code, which is just calling a function. And in Kotlin it will be pretty much similar because, I mean, Kotlin also can call functions. So visually it will look almost the same. And the way to implement it, we can have this Android binary function, which we are calling as an extension, a function to the context object that we created, and then just define a list of arguments. And in the body of this function, we will just construct a bunch of tree nodes, which will then add to our syntax tree. Yeah, and next cool feature of Kotlin is indexed access operator. So if you remember, like when you're working with list, when we're using this square brackets to access elements by index, so this is an indexed access operator, and we can use it somehow in our DSL, and let's see how can we use it. So we have another feature in Starlark or Python is defining list expressions. So this is just a simple list that consists of 3 elements. And in our DSL, we can do pretty much the same thing. Unfortunately, Kotlin does not allow to use just square brackets without anything. So we kind of creating here our own operator list, which will serve the same purpose. And inside this new operator, how it works is that we're creating just another dummy object, like list expression builder. And we have a property inside of our DSL, which returns this object. And then we overriding this square brackets operator as an extension function to this, again, dummy object. And this is how it provides us those square brackets that are applied to this list, which is our newly created custom operator. Yeah, another cool feature of Kotlin is a property delegation, and it also can be used in many ways, and let's see how we can use in our DSL. So, for example, in Starlark or in Python, we can see, we can assign some variables and define some variables. So we have a string variable, we have a list variable, and dictionary variable. And in Kotlin, we can do pretty much the same. Just by using, first we are defining those variables as well, because we need then to reference it somehow. So first we're defining this variable, and then we can pass it to the function. And we need to generate something like this. This is why we need val, so that we can reference it. And then we're using by operator to kind of replicate the assignment. And you might ask, okay, so why don't we use just regular assignment, and why do we need this by operator? And the thing is that regular assignment will be executed on the level of Kotlin. So when the program will be executed, Kotlin just have this myString variable, which already will have this value. However, we need to generate this assignment operation instead of calculating it on Kotlin side. And that's why we can have this by operator, which inside will know how to generate this assignment sign and put it in place. And in the end, all those components like myString, mylist, mydictionary, they will all have different types, like string reference, list reference, and dictionary reference, which are again part of syntax tree, which are separate nodes. And if I see the implementation of those nodes, like list reference implements interface list, which means that everything that is a list reference, we can put it to our function that takes, for example, a list argument. And this way we can achieve a type safety. And we don't need to, basically we can just use custom types and assume they are just regular list. And yeah, that's the idea. And the same with dictionaries. So we have dictionary reference, like in Starlark we have dictionary, but it's similar to map in Kotlin, and that's why we implement this interface. And it would be cool to do the same with string reference, but here's the catch. If you just extend the string class, it's not possible because string is final class. But we need to somehow pass string references everywhere where string is expected, so what should we do? And the answer here is that we can use char sequence, and in Kotlin, in Java, every string implements a char sequence, so that we can assume that all string types in our DSL will be represented as char sequences, and in this case we can implement it as well. And if going back to our DSL, so here we defined our variables like name, src, etc. And we are putting them into our Android binary function that expects just list, dictionary, etc. Yeah, and final tweak inside this Android binary function that we already defined is that we need to replace all the string occurrences with char sequence so that it will work and compile. And this is how we can achieve type safety of our DSL, because it's very important during the code generation that everything that we write here is actually valid code that can produce and generate valid code. And this is how we can achieve it from type safety perspective. So, okay, we just discussed some basic components of the DSL, but let's discuss another thing. So, imagine that this Android binary function, it's supported by either Starlark developers or some library developers who are doing this, who are maintaining this function and library. And let's imagine that we created our DSL, but somebody after that adds new argument to this function. And what should we do? Because with our current version of DSL, it's impossible to generate this argument because it doesn't exist yet. So in this case, we can introduce kind of dynamic function arguments. And here, as you can see, we have a bit of a difference. So first, when we call Android binary function, we are using curly brackets. And then inside, this new argument is marked just as a string. And then we use some weird operator, which looks almost like assignment operator, but with those weird backticks. And yeah, we are not able to use just a regular assignment operator because, I mean, it has specific purpose in Kotlin. However, we can replicate it very closely. And the way how it works inside is that if you're using those curly brackets, we have another case of using some context. The same way as we used with build.bazel function, we can use the same here. And yeah, inside of this context, we can just have a bunch of arguments that are defined that we can use for our function. And this assignment operator, this is just a simple Kotlin function. So Kotlin has this, provides this ability to name functions almost the way you want, like works almost every time, except a couple of exceptions. Yeah, but the main idea is here just use backticks, and inside of this backticks just put every name that you want, and we can put here like assignment operator. And we just make this function as infix so that two of its arguments can be like one on the left side and one on the right side. And yeah, this is how it can be achieved. And inside, again, we're just creating a bunch of new tree nodes that we add to our tree. Yeah, and okay, arguments are cool, but what if somebody adds new function to the library? So what should we do in this case? And the answer is pretty similar. We can just have this function call, and the name of the function can be used as a string. And again, we have this like curly brackets, and all the arguments inside of those curly brackets will be implemented the same way as we just like discussed for the arguments. And in the implementation, how this like custom function A can be implemented, it's just an extension function to string, but it's not just every function. It's an invoke function, which is operator function, which means that we can like kind of apply the lambda function after the string, which will help us to achieve this visual similarity with function calls. So that we have string and then curly brackets. And inside we have the same thing. We are creating new type of context. And this function called context object, it will provide some new functionality that's available only inside of this curly brackets for this specific function call. Yeah, and again, we're just creating new tree node. So yeah, now let's see how those elements can be combined together, because in real world cases, code is much more complex than just a simple function calls and variable assignments. We can have some new operations, for example, like concatenations. So usually when we write code, the source of our data can be combined from multiple. So first we have, in this Starlark example, we have the source files, which is a list. And then when we pass it to Android binary function call, we adding some new part of the list using a plus operator. And this means that we need to implement something similar in our DSL. So yeah, again, we can, as you remember, we can name our functions the way we want. So we can just create a new function which will be called plus, but with those backticks. And it will help us to generate this plus operation. And again, similarly, we cannot just use a regular plus operator. This code will compile, but in the end, the generated code will consist of only one list. But the reason why we're using this plus with backticks is to actually generate this plus operation on Starlark level. And yeah, it works pretty the same. We have a list, and we are using an extension function to this list, which is called just plus. And inside we are creating another type of tree node, which is list binary operation. Why it's specifically list binary operation? Because it needs to conform to the list type, which means that everywhere where list is expected, this operation should be compilable and should be able to pass it there. And yeah, and inside of this list binary operation, you have a left node, operand, and right node, which also can be, you can have multiple binary operations nested together if you have like multiple consecutive plus operations. Yeah, and inside we are doing just like this. But sometimes it all works good, but sometimes you can have problems, like context conflicts. So if you remember, we have those context objects which work as this inside the context. So we are defining here the function called Android binary. But here we have a problem. So inside of the Starlark file context, the outer context, we have Android binary function available. And technically, in our DSL, it is possible to call Android binary while we are calling Android binary, which is a not valid code in Starlark, because this is not something you can do. You can call functions only that return results and assign result to the argument, but not like this. But still in Kotlin it's compilable, but it's not something we want, and there is a way to prevent this. And the answer to this question, how to prevent it, it's another feature of Kotlin DSLs, which is a DSL marker. Basically, this is something that you can mark your context objects, and then the compiler and the IDE, it will catch and it will find if you are using the context right, and it will make the code that we just described not compilable. So in order to use it, we just need to mark our context objects with an annotation that we just created, a language scope. And then compiler will track how we use this context, and you are not able to use something from the outer context inside of the inner context, which is something that we need, because we need like a full control of what we want to do in this context and what we shouldn't. However, there is another problem. We have this plus operation, which is also available in the outer context, but not in the inner context. And I mean, it's not a good idea to just implement this plus operator twice in both contexts, because it's not something we want. But for now, this code will not compile. So yeah, and we need to also find a solution for this. And to do this, we need to restructure our DSL, and we need to introduce kind of an architecture to our DSL. So what I mean by this is that we have a bunch of features in our DSL, like concatenations features, like function calls feature, where basically each feature requires overriding some operators, adding some new functions and stuff like that. What we can do is that we can create a separate interface for each of the features that we have in our DSL. So in this example, we can have concatenations feature, and we can implement only those functions that are related to these features. In this case, it will be just pluses. And then each of our context, it will implement this interface. And we can have even implementation inside of this interface. So basically, this will be an interface with default implementations. And now both Starlark file context and Android binary context have those operators available to them. And in this case, including our DSL markers and all the restrictions of context, we are still able to use the plus operator, because now Android binary context implements this specific interface and it has this functionality. And it can work even on more levels. So for example, we have another argument which is dictionary. So in this case, we have this manifest values argument, which we assign the value. And the value is dictionary, so open curly braces, and we have new context inside, which is a dictionary context. And inside there will be available only operators that are needed for dictionaries. And in this case, we have a new operator, which is like mapping. So in Kotlin, there is a to function, but this one is modified because on the left and on the right, we have those plus operators. But as you can see, those plus operators on the left and on the right, they are just regular plus operators that are implemented on other levels. And this way, with using those interfaces, we can just have a full control of what's available and what is not available inside of every part of our DSL, which is something that we need, because we need to prevent any failures and any errors or like invalid code on the early stages. So we shouldn't wait while the Starlark code will be generated, but we can do it as early as possible. Yeah, so let's talk about some additional features briefly, I think. We'll not take a look in the implementations because the idea would be similar. We're just using some Starlark, some Kotlin elements to implement the DSL, and inside we're just creating new tree nodes in some way. For example, in Starlark and in Python, we have a list comprehension feature, which is kind of fancy builders for lists. And we can do similarly for Kotlin DSL. Of course, this is not like one-by-one relation, but it's pretty similar and pretty close. So basically how it works. For each file in the list that we have, we will perform some operation. And the idea in this particular example is that we have a list of some strings, and in the end of each string we are just adding .java suffix. And the resulting list will have those file names. And yeah, again, we can implement it the way that we have this take function which has curly brackets, and again it will have another context object, and this like first it parameter will have a char sequence type, or like string type. And why is this? Is because we have a list of strings. So when we have a list of strings, it's possible to identify the type of the item. But the same can work with list of numbers, list of booleans, and even list of lists. And yeah, just also want to briefly discuss how can we apply KSP in this case, because we might have another problem. So we have our function call, right? It has 3 arguments, but in real life it has like around 10 or even like 15. So we have large functions. Some of them, many of the arguments are optional, but they should be all there. And so in the real example, we have this amount of code for each function, but this is not all. We have also this amount, because if you remember, we had function calls with curly brackets and function calls with round brackets, and it works differently, like completely differently. And we need to provide both operations, because in some cases people would want to add some custom arguments, in others don't. So yeah, this is like real world example of a function, and a library can have like hundreds of those functions, or like maybe even a bit less, but manually writing this code is not something we want to do, but we can automate this process, and we can use Kotlin simple processing to do it. And the way how can we do it is the following. We can define an interface, which will be Android binary, and it will correspond to our function call, Android binary. And we can create our custom annotation, library function. It will have argument like Android binary, which will define the name of the function. And then our Kotlin simple processor can just go through every property in this interface and just figure out like what arguments it will have. So in this case, every property defined inside of the interface will correspond to the arguments of the function. And we have name, we have its type, we have manifest, it has its type, and so on and so forth. And yeah, this way, all of this code, so in this case we just need to define an interface and just list properties which correspond to every argument. For example, we can have 20 of them. And all of this horrible code will be generated automatically. Yeah, and now finally let's take a look about on a bit more advanced and complex use cases, how it can be used in practice, because yeah, usually code looks a bit more complex. So here is the real world example. So this code helps to build Android projects that use data binding, and this can be built with Bazel. But here, this is a fragment of this code. And what's happening here? So we have this square brackets, which means this is a list comprehension. And then for each element in the list, so we have a list which lists the list of files. For each element, we have the item, like specific file. We can work with it. For each element, we will call the function. And inside of this function, we can, for example, concatenate name from multiple arguments. We can use range operator for slices. I mean, this is still Starlark code, so yeah, it has another feature which is called slices, which basically like some modifying, like getting sub-arrays and sub-strings, for example, in this case. Yeah, so, and all of this can be like put together, and it adds complexity. And here is the Kotlin code that replicates this syntax. So again, this is the Starlark code, and the Kotlin code, it's not like identical, but it's pretty close. And here we have, again, we have a list comprehension with our like custom take operator that we just discussed. Then we are defining the list of some elements, and it's important to know that this list is a list of strings, and the DSL understands this. And this file object inside of the curly brackets, it will have type of string. And then inside, we can again call the general function. So this is just another function which we can define. We can use concatenations here as well. And range operator in Kotlin looks pretty similar to how slices work in Python or Starlark. So again, we can replicate this syntax here. So yeah, the main idea and like what in this talk we just seen a specific example of DSL, and I understand that there are not many people in this room would want to generate Starlark code in their life, but all these concepts can be applied to different types of DSLs. And the main thing here is that we might want to apply different Kotlin syntax elements in a non-conventional ways, and this is fine. If that serves the purpose and it can improve the DSL, why not use them this way? And yeah, the main thing here is to experiment, because those things, you just need to try them this way and that way and find what fits better for your use case. And yeah, so if you want to see how it works under the hood, this thing is implemented on a GitHub, in the project which is called Irene. This is again project for migrating Gradle projects to Bazel, and inside it uses this tool to generate Starlark code. So yeah, this is it from me. Thank you for attention.